this point in the course, you should have a sense of what the mean and standard deviation are and understand the importance of the normal distribution. In this lecture, I will discuss how you can use your knowledge of the mean and standard deviation of a set of scores to make inferences about data. We will therefore be moving from discussing descriptive statistics to inferential statistics. After completing this lesson, you will be able to achieve the following learning outcomes. While some of these may be a review, others may be new to you. These learning outcomes focus on understanding what the normal curve is and learning how to use it to predict the likelihood of future events through the calculation of z-scores. I'll discuss each of these points in turn. Many statisticians rely heavily on the normal distribution because it can be a useful tool for making predictions. This is because when a distribution is normal, we know that 34.13% of the scores lie above or below one standard deviation of the mean. An additional 13.59% of the scores lie 2 standard deviations above or below the mean, and only 2.28% of the scores lie outside that range. Another way to think of this is using the 68-95-99 rule, which essentially says the same thing, that within one standard deviation above and below the mean, you can expect to find approximately 68% of the scores in the distribution. Within 2 standard deviations above and below the mean, you can expect to find approximately 95% of the scores in the distribution. And within 3 standard deviations above and below the mean, you can expect to find almost all of the scores in the distribution. The cool thing about this rule is that when a distribution is normal, just by knowing the mean and standard deviation of a variable, you can predict the probability associated with any particular value. For example, let's say we had an average score on an exam with a mean of 65 and a standard deviation of 10. This means that 68% of the scores lie between 55 to 75 points. 95% of the scores lie between 45 to 85 points. And almost all the scores lie between 35 to 95 points. Another way of interpreting this data is that you have a 32% chance, which is 100 minus 68%, of getting a score higher than 75 or lower than 55 on the exam. A 5% chance, which is 100 minus 95%, of getting a score greater than 85 or less than 45 on the exam, and less than a 1% chance, which is 100 minus 99%, of getting a score greater than 95 or less than 35. If a student had a score higher than 95, they would be exceptionally different from other students in the class, as would a student who got a grade lower than 35. You can see how the 68-95-99 rule can come in handy in identifying exceptional cases and predicting the likelihood of events. However, this rule is a bit limited if we're interested in predicting the precise probability of a specific score. For example, it is hard to determine the differences in the probabilities of getting a 78 or an 80 on the exam, because neither of these values fall perfectly at the 1, 2, or 3 standard deviation intervals of the mean. One way to get around such problems is through the calculation of z-scores. Z-scores help us translate raw scores into standard deviation units. Several years ago, a group of statisticians determined the percentages that fell under the curve of the normal distribution at each point on the x-axis. This information is recorded in the z-score tables. Z-score tables are very popular and can be found in the back of any statistics textbook. When reading the z-score tables, you will see references made to column B and column C. As shown in the graphics here, column B represents the area under the curve that corresponds to the distance between the mean and the calculated z-score, whereas column C represents the area under the curve that lies beyond the calculated z-score. Here is what the z-score tables will look like. The values of z will be in column A and the corresponding percentages will be listed in columns B and C. There are two main formulae which we'll use in relation to z-scores. The first formula relates to computing z-scores, which can then be used to find the probability associated with a specific value of x, whereas the second relates to finding a specific value of x for any given probability. You can see here that the second formula is simply a variation on the first. Let's put these formula in context with a sample question. This example was taken from a question related to your reading from the Fox text. The question is asking to identify if the scores received by Officer 1 and 2 are high enough to be considered for promotion. The question provides the mean and standard deviation of the distribution of scores, along with the observed values of Officer 1 and 2. Using the first formula for z-score calculations, we can determine the probability that Officer 1 would receive a score of 76 and Officer 2 would receive a score of 52. Let's start with Officer 1. By plugging in the values for the mean, observed score, and standard deviation, we can see that the grade of 76 received by Officer 1 on the exam was 1.27 standard deviations above the mean. I'll show you in a second how to identify the specific probability associated with the z-score value, but this question has already stated that the scores with a z-score of 0.83 or above are high enough for promotion. This means that the answer to Part A in this question would be yes. To answer Part B, you would follow the same procedure to calculate the z-score for Officer 2 to see if he would qualify for promotion. However, instead of having to calculate z-scores for each officer, let's take a simpler approach. This would involve using the second formula mentioned earlier. The question mentions the mean, standard deviation, and the z-score used for the cutoff. This means that we can easily determine the cutoff score that should be used for all officers by plugging these values in the equation above. By adding in the mean, z-score, and standard deviation, we can see that any officer with a score of 71.13 or lower should not be considered for promotion. This means that Officer 1 should be considered for promotion, whereas Officer 2 should not. A key point I'll explain is how they knew scoring higher than 80% of those taking the exam corresponded to a z-score of 0.83. To answer this question, we will need to use the z-score tables I mentioned earlier. In the example, we needed to know what z-score corresponds to scoring higher than 80% of those taking the exam. This means that only 20% of the sample would have a z-score higher than this value. If we look at the z-score tables, we can see that in column C, the area beyond z or higher than z, 20.33% corresponds to a z-score of 0.83. Another way to think of this is that at a z-score of 0.83, only 20% of the sample would have a score higher than this value, whereas only 80% of the sample would have a score lower than this value. Let's practice using the z-score tables with a variation on our example. Let's say that we had too many officers qualify for the promotion and decided to raise the bar so that only officers with scores higher than 90% were considered. This means that we'll now need to determine what z-score corresponds to 90%. Using the z-score tables, we can find that in column C, the value closest to 10% corresponds to a z-score of 1.28. We can now plug these values into the equation listed here to find what the new cutoff for the exams will be. By adding the mean, z-score, and standard deviation, we can see that any officer with a score of 76.08 or lower should not be considered for promotion. This means that Officer 1 should not be considered for promotion, nor Officer 2. Once again, let's say instead of an 80% cutoff, we're interested in evaluating whether or not the officers' scores were significantly different from each other. In order to do this, we would have to change our z-score to reflect the score that corresponds to 95%. The fastest way to do this without using the z-score tables is to apply our knowledge of the normal distribution. Using the 68, 95, 99% rule, we know that approximately 68% of the scores in a distribution lie within one standard deviation of the mean, whereas approximately 95% of the scores lie within two standard deviations of the mean, otherwise known as the range of significance. By changing the z-score to 2, we can quickly get a sense of the cutoffs we should use to determine if the officer's scores are significantly different from the rest. Like before, we will solve for x by plugging in the mean, z-score, and standard deviation, which would give us the following equation. These results showed that if an officer got an 84 on the test, their score would be significantly higher than all other officers. Instead of looking at a positive 2, we could also change the valence of the z-score to negative 2 to determine the lower end cutoff. These results are summarized in the graph shown here. Here we can see that on average, officers scored a 62 on the test. Officers with scores higher than 84 did significantly better than all others doing the test, whereas officers with scores lower than 40 did significantly worse than all others taking the test. Given what we know about z-scores, let's explore what other questions we can answer by integrating our knowledge of probability. Presented here are three of the most popular rules of probability. The rule of complementary events is applied when we know the probability of x but are interested in the probability of x not occurring. As shown in the examples here, this is equal to 1 minus the probability of the event happening. The addition rule of probability is applied when we need to determine the probability of x or y happening. Note that the addition rule is not limited to only two events. As shown in the examples here, these probabilities are determined by adding the probability of x to the probability of y. On the other hand, the multiplication rule of probability is applied when we need to determine the probability of x and y happening. Note that similar to the addition rule, the multiplication rule is not limited to only two events. Given that the chance of both x and y occurring at the same time would be lower than the chance of either event occurring, we would expect the probability to be much lower. As shown in the examples here, these probabilities are therefore determined by multiplying the probability of x with the probability of y. In summary, these are the key theoretical concepts that you will need to know in this course as they relate to probability and the normal distribution.